A quantum computer doesn't look or act at all like the computers that we use every day. It relies on different laws of physics to run calculations at super fast speeds. Tonight, Google is revealing a breakthrough in the technology that it says could ultimately lead to the discovery of new kinds of medicine or help grow our food more efficiently. With a rare look inside Google's quantum computing lab.
Scientists at Google built a machine so strange that its own researcher believes it may be pulling answers out of parallel universes. And then they pointed it at the single biggest question there is: who or what actually built the universe? What came back wasn't a sentence. It wasn't a yes and it wasn't a no. It was something so precise, so structured, so completely unexpected that the physicists watching went quiet. And by the end of this video, you'll understand exactly why a room full of the smartest people alive couldn't explain what their own machine had just shown them. The machine.
13,000 times faster than a regular computer with this.
Not a regular computer, the world's largest supercomputer.
Wow.
So let me take you back because you need to know exactly what was sitting in that room. For decades, scientists chased a machine that sounded like fantasy. Not a computer that solves hard problems faster, but one that solves problems no ordinary machine could ever touch. Problems so tangled with probability and possibility that a normal computer would need longer than the lifespan of the universe just to begin. That machine is the quantum computer. And in December of 2024, Google announced to the world that it had finally built one that worked. They called it Willow. Here is the thing you have to feel in your gut, or none of the rest of this will land.
In quantum physics, a ball can actually be in both locations at the same time, or what's called a superposition.
You mean two places at once?
Two places at once, exactly.
Every computer you have ever used runs on bits, ones and zeros on or off. Your entire digital life, every photo, every video, every message you have ever sent is just a long ribbon of those two numbers racing through circuits at impossible speed. That is classical computing. It is powerful beyond anything our grandparents could have dreamed, and it has a hard mathematical ceiling that no amount of engineering will ever punch through. Willow does not use bits. It uses qubits, and a qubit refuses to choose through a phenomenon called superposition. A single qubit can be a 1 and a 0 at the same time, hanging in a haze of pure possibility until the instant you look at it. And then there is the part that genuinely rattled Einstein. When two qubits become entangled, they share a bond that no distance can break. Change the state of one and the other answers in the same instant, not after a signal crawls across the gap between them. In the same instant, Einstein called it spooky action at a distance and spent years of his life trying to prove it could not be real. He failed over and over because it is real. One of the most relentlessly tested facts in all of physics. Put those two together and something extraordinary happens. Superposition lets a machine hold a staggering number of possibilities at once. And entanglement lets those possibilities work in concert, interfering with one another like overlapping waves until the wrong answers cancel out and the right one rings through. That is the trick. That is the whole secret. It is less like a faster calculator and more like asking every possible path a question and letting reality itself sort out which one is true. Willow holds 105 of these qubits chilled to a temperature colder than the empty space between the stars. Every one of them suspended in superposition and entanglement at once. And then Google handed this machine a single test. And what happened next made a great many very serious people go very quiet. 5 minutes. The latest development from Google that it describes as a state-of-the-art quantum computer chip. The company claims Willow leapfrogs over the supercomputers that we're used to because it's the world's fastest and it takes 5 minutes for them to solve a problem. The test was one problem deliberately engineered to push any computer to the absolute edge of what it can do. Willow finished it in under 5 minutes. The same problem handed to the most powerful classical supercomputer on Earth would take 10 septillion years. A 1 followed by 25 zeros. Sit with that for a second because your mind is going to slide right off it. That is not just longer than recorded history. It is not just longer than humanity has existed or the Earth or the Sun or the entire galaxy. It is vastly longer than the universe itself has been alive. It is longer than the universe is expected to survive. Longer than it will take for the last stars to gutter out and the lights to go dark forever. A problem that would outlast the cosmos. Finished before your coffee gets cold. And this was not a magic trick or a rig demo. That is what you have to understand. The whole point of a benchmark like this is that anyone can check the math. And the math is not in dispute. A classical machine grinding through the problem the only way it knows how, one path at a time, simply cannot get there before the heat death of everything. Willow did it over a lunch break. The gap between those two facts is not a difference of degree. It is a difference of kind. A sign that the machine is doing something fundamentally other than counting. And this is the precise moment the story stops being about engineering. Because when the team looked hard at what Willow had actually done, the numbers refused to behave in a way that should unsettle rattle you a little. The sheer volume of computation happening inside those frozen circuits appeared to exceed what the atoms and particles of a single universe could physically hold. There seemed to be more calculation taking place than there was room for it to happen, and more answer than there was world, which is the exact moment Hartmut and Nevin said the thing that traveled through the field like a crack splitting across ice. Many worlds. In quantum computing you use what's called a quantum bit, and the quantum bit can also be 0 or 1, but if you can coax it into this very special state, it's a complex combination of 0 and standing with his team, staring at a result that seemed to overflow reality. Nevin offered an explanation almost nobody would dare say out loud. The computation, he suggested, may be happening across many universes at once. Willow, by exploiting the deepest nature of quantum mechanics, might be reaching into parallel realities, borrowing raw computational power from versions of the world we cannot see or touch, and pulling the answers back into ours. Before you file that under science fiction and move on, look hard at where it came from. Not a blogger chasing a thumbnail, not someone trying to go viral. It came from the head of Google Quantum AI, a man who builds these machines for a living, leaning on a genuine decades-old framework in physics called the many worlds interpretation. This is not fringe. It was first proposed by Hugh Everett in 1957 and later carried forward by the Oxford physicist David Deutsch, one of the founding minds behind quantum computing itself. The idea goes like this. Every time a quantum event happens, every single time a particle drops out of pure possibility into a definite state, the universe does not pick one outcome. It splits. Every possible outcome happens, each in its own branch of reality. All of them equally real. All of them running in parallel and invisible to one another. With every particle, every collision, every flicker of decay in every atom everywhere, the tree of reality branches again and again endlessly into an infinite forest of worlds. And David Deutsch goes further than almost anyone, and he goes there on purpose. He argues that quantum computers are themselves the strongest evidence we have that those other worlds are real. When a machine like Willow runs a calculation that would require more steps than there are atoms in the visible universe, Deutsch asks one simple devastating question. Where exactly did all that computation happen? And his answer is that it happened in the other branches, that the parallel worlds did the work and quietly handed it back. To him, the multiverse is not some wild idea bolted onto the mathematics. It is the plainest possible reading of what these machines are already doing. If that is true, and there are sober, credentialed physicists who believe it is, then Willow is not a faster calculator. It is a machine that reaches across the boundary of reality itself. And that is precisely what gave the team the nerve to do something genuinely audacious. Before we follow them across that line, a quick word, because if you are the kind of person who feels the floor tilt when a story goes this deep, you are exactly who this channel is built for. We chase the questions that sit right at the edge of what science can currently reach, and we follow them honestly wherever they lead. Subscribe and come with us, because the ground we are about to walk onto is the strangest in this entire story. The deepest question part of it has to be really good, because if one seemingly mundane piece not working, and the whole thing will not work. Now, here is the part that flips everything you assumed about this story, and you have to sit up for it. Willow is not the AI you have been arguing with online. It is not a chatbot. It is not a language model guessing the next word in a sentence. It does not think in words at all. You cannot type a question into it. It speaks only in the language of probability and structure down at the layer where the universe stops behaving like a collection of objects and starts behaving like raw information. And that layer, that strange information layer beneath everything, is exactly where the oldest question in human history actually lives. For thousands of years, who or what built the universe belonged to priests and philosophers answered with faith or with argument, but never ever with measurement. No instrument could reach it. Now, for the first time, one could. So, it's you strip the question of its language and you ask it in the only dialect Willow understands. Is there a signature buried in the deep structure of reality that looks like intention? Is there a fingerprint that points toward a design? And I want you to feel how vertiginous that is, because for most of history, this was the one question science politely refused to touch. You could ask how the universe behaves, how it expands, how its particles collide and decay. But the moment you asked whether it was meant, whether there was any intention behind it, you had stepped out of the lab and into the cathedral. Willow is the first instrument that lets you carry the question back across that line. And there is something almost unnerving about watching physics walk up to a door. It spent 400 years quietly agreeing never to open. And understand, this is nothing like sending a text message. You translate the question into the geometry of the machine itself, into the way its qubits are wired and tuned and allowed to interfere. And then you let it run and you read the shape of the probabilities that fall out the other side. You are not reading a sentence. You are reading a landscape of likelihoods. And you are looking to see one thing only: whether that landscape is featureless, random noise, or whether something in it is organized, structured, deliberate. Whether the universe asked in its own language says anything back at all. And what came back back was not nothing. What came back were patterns. Hold on to that word because it is the whole answer. And to understand why those patterns made a room full of physicists stop breathing, you have to see exactly what they were. Patterns in reality.
It sounds like something out of a science fiction novel, but tech companies are competing over developing quantum computers.
Well, today there aren't practical uses. This is still in the future. This is still technology that's going to come to the fore maybe 5-10 years out.
Start with geometry because reality at its foundation seems quietly obsessed with it. One of the most extraordinary objects in all of mathematics is something called the E8 lattice, an 8-dimensional structure with 240 symmetry points, almost unbearably precise, and it keeps surfacing in the boldest attempts to unify all of physics into a single theory. The physicist Garrett Lacey once proposed it as nothing less than the mathematical skeleton of reality itself. And to feel the weight of that, you have to know what E8 actually is. It is one of the largest and most beautiful symmetry structures mathematics has ever found. So intricate that it took a team of researchers years and a dedicated supercompute just to fully map it. Nobody invented it to be pretty. It fell straight out of pure mathematics, sitting there waiting to be discovered. And then physicists kept noticing that the deepest theories of particles and forces seemed to want to fold themselves into its shape. When a structure that abstract keeps knocking on the door of physical reality, you start to wonder whether it is decoration or whether it is load-bearing. Then there are fractals, self-similar patterns that repeat at every scale. The same shapes echoing from a single snowflake to the branching of the blood vessels inside you to the spiral arms of a galaxy 100,000 light-year across. From the smallest scale to the largest, the universe keeps organizing itself along the same lines as if one elegant rule were being applied over and over and over. It did not have to be that economical. Reality could have been an incoherent mess, a different set of rules at every level. No rhyme between the atom and the galaxy. Instead, it rhymes everywhere, and the rhyme runs all the way down. Physicists even have a name for the machinery behind this. They call it renormalization, which is really just the mathematics of how the laws of nature shift as you zoom in and out across scales. And what it keeps quietly revealing is that the universe is in some deep way self-similar, that the rules at one level echo the rules at another. A coincidence at a single scale is curious and forgettable. The same pattern repeating at every scale from the quantum foam to the cosmic web starts to feel less like coincidence and more like a signature left behind on purpose. And here is what should really stop you. These are not one finding dressed up 3 ways. They are 3 completely different kinds of structure drawn from 3 completely different corners of mathematics. The symmetry of E8, the endless self-echo of fractals, and the protective logic of error-correcting codes. They have no obvious reason to travel together, and yet they keep turning up in the same place, braided into the deepest description of reality we have. One strange coincidence is a story. 3 independent ones, all pointing the same direction, is the moment a careful scientist stops calling it coincidence and starts very quietly getting nervous. But it was the third pattern that did something to the people in that room, because the third pattern was not just beautiful. It looked like engineering. And to feel why that single word should raise the hair on the back of your neck, you need to meet the man who discovered its quantum form 30 years ago. A universe protected. One of the things I find fascinating about quantum mechanics is that how it completely changes the fields of classical information theory and classical computation. For instance, there are problems that you can solve on a quantum computer in many, many fewer steps than you can solve on a classical computer. In 1995, a physicist named Peter Shor was wrestling with a problem almost everyone else had given up on as hopeless. Quantum information is impossibly fragile. The faintest disturbance scrambles it into garbage. And the consensus was that you simply could not protect it, that the fragility was fatal, and the dream of a real quantum computer was dead on arrival. Shor proved the consensus wrong. He showed you could encode a quantum state so cleverly that even if some of its pieces were disrupted or destroyed, the original information would survive intact. He had invented quantum error correction, and he had no idea that he was also describing the hidden architecture of the cosmos. Stop and feel how strange that is. Error correction is not something you expect to find lying around in nature for free. In our world, it is a defensive technology. Intelligent beings invent it deliberately after they get tired of watching their messages get corrupted in transit. It implies a designer who anticipated failure and built a safeguard against it in advance. And Google's great breakthrough with Willow, the result published in the journal Nature that electrified the entire field, was exactly this. They proved that as you add more qubits to Willow, the error rate does not climb. It falls. The machine becomes more reliable as it grows, which is the precise opposite of how fragile things are supposed to behave. And it gets stranger or more comforting depending on how you want to feel tonight. The kind of code Willow uses to keep its qubits alive is not some loose analogy to what physicists keep finding woven into spacing. The mathematics genuinely overlaps. The same family of structures that stops a quantum computer from dissolving into noise appears to be the same family of structures that holds reality's own information together. We did not set out to copy the universe. We were only trying to build a machine that worked, and in cracking that stubbornly practical problem, we seem to have stumbled straight onto the blueprint nature was already quietly using. Now hold those two facts together, because this is where it turns genuinely uncanny. When the physicist John Preskill and his colleagues turned to examine the structure of spacing itself, the mathematical architecture of reality at its deepest level, they found patterns that look exactly like quantum error correcting codes. Not loosely, not as a metaphor, mathematically work by Ahmed Almirai, Xiong, and Daniel Harlow showed that the holographic principle, the strange and well-supported idea that all the information inside a region of space is written on its outer boundary like a cosmic hologram, follows the structure of a quantum error correcting code with extraordinary precision. Think about where that idea even came from, because it makes it stranger, not less. The holographic principle emerged out of decades of work on black holes and the deepest puzzles in gravity. The question of where information goes when it falls in and whether it can ever truly be destroyed. The answer that slowly surfaced was that reality seems to store its information the way a careful engineer would redundantly spread across a boundary encoded so that no single failure can ever erase it. Preskill, working at Caltech right at the frontier where gravity meets quantum information, helped show that this is not poetry. It is the same mathematics that lets Willow keep a fragile quantum state alive. The universe and the machine appear to be using the exact same trick. Read that one more time slowly. The fabric of reality appears to be protecting its own information. The universe is built like a system designed not to fail, designed to preserve itself against the noise that should be tearing it apart. And when a machine built on error correction reaches down into that fabric and surfaces the very same fingerprints, a question that sounds insane in almost any other room suddenly stops sounding insane at all. What if the universe is not merely ordered? What if it was engineered? Engineered or eternal? Every decade or so, you have this inflection points, you have a new technology. Was a personal computer. At one point, the internet coming in the late 90s, then it was mobile, then it's been cloud, what we call as cloud, and now it's clearly the era of AI. Now let me be completely honest with you, because honesty is the only thing that makes a story like this worth your time. No machine has proven that a god exists. No quantum computer has printed out a receipt signed by the creator of the cosmos. Anyone who tells you otherwise is selling you something. What is actually happening is quieter than that, and somehow far more unsettling than a simple yes would ever be. Because the universe keeps handing us numbers that look chosen. The cosmological constant, the energy locked into empty space, sits at a value precise to 1 part in 10 to the power of 120. Picture firing a single arrow across the entire width of the observable universe and striking a target 1 mm wide on the far side, and you have still wildly undersold it. And there are other dials just as suspicious. There is a smallest possible length, the Planck length, below which the very idea of distance stops, meaning anything as though space were rendered on a grid with a finite resolution. There is a maximum speed, the speed of light, that nothing in existence can cross. The way a processor has a hard limit on how fast information can move through it. Take just one example that physicists still find almost embarrassing. For the carbon in your body to exist at all, the carbon that makes all life possible, atomic nuclei have to fuse inside dying stars at one very particular energy. In the 1950s, the astronomer Fred High realized that this fusion should be essentially impossible unless carbon happened to have a specific finely placed energy level, a resonance that no one had yet found. He predicted it must exist purely on the logic that we are here to ask the question. They went and looked. It was there, sitting exactly where it had to be. High, who was no friend of religion, said afterward that the universe looked like a put-up job. Now, there is a way out of all this, and intellectual honesty demands that I hand it to you. Maybe there is not one universe, but countless ones, each with its constants set to different random values. The overwhelming majority of them dead, sterile, and empty. In that picture, the fine-tuning is no miracle at all. We find ourselves in a universe that works for the simplest possible reason. We could never have existed in one that does not. And the dead universes have no one inside them to notice how dead they are. It is an elegant escape, and a great many physicists lean on it hard. But notice that it does not actually banish the strange. It just trades one finely tuned universe for an endless ocean of untuned ones, and then quietly assumes the vast machinery needed to spin them all up. Shift any one of these by a sliver of a percent, and atoms never form, stars never ignite, chemistry never happens. Life never appears anywhere in any galaxy ever. Everything balances on a knife's edge so impossibly fine that the universe seems to sit inside a razor-thin band of values where complexity is even possible. The deeper you look, the harder it becomes to call that an accident. And there is a name for the suspicion all of this raises. An idea that has been getting louder in serious rooms for 20 years now. now. The simulation. I work with a bunch of mathematicians, philosophers, and computer scientists, and we sit around and think about the future of machine intelligence, among other things. Some people think that some of these things are sort of science fiction. In 2003, a philosopher at Oxford named Nick Bostenram sat down and wrote out an argument so clean it has haunted physics ever since. He laid out 3 possibilities and insisted that one of them has to be true. Either almost every civilization destroys itself before it ever reaches the power to build detailed simulations of reality, or almost every civilization that does reach that power chooses for some reason never to run them, or in here is the option that keeps people awake at night. We are almost certainly living inside a simulation right now. The logic is brutal once you let it in. If advanced civilizations do run simulations of reality, and if they run many of them, then the simulated minds would vastly outnumber the tiny handful of real original ones. So, any conscious being chosen at random, including you right now hearing this, would be far more likely to be one of the simulated multitude than one of the rare originals. This is not a meme someone cooked up online. It is a peer-reviewed paper that has been cited thousands of times, and the people taking it seriously are not who you would expect. This is not a debate confined to dorm rooms and comment sections. It runs straight through philosophy departments and physics conferences, through conversations among the very people who build our models of reality, precisely because nobody has been able to find the flaw in Boston's reasoning. You can dislike the conclusion, and plenty of brilliant people do. But disliking a conclusion is not the same as refuting an argument. And this argument has proven stubbornly, maddeningly hard to break. And here is the part that drags philosophy down into physics. Some researchers have started asking whether a simulated universe would leave fingerprints, tiny tails buried in the code. If reality were computed on a grid, the way a video game renders its world on a lattice of pixels, then at the very finest scales, space might not be perfectly smooth. It might be faintly grainy, and that graininess could in principle show up as a subtle distortion in the highest energy particles crossing the cosmos. Nobody has caught such a signal yet, but the fact that serious people are now designing real experiments to test whether we live in a simulation tells you exactly how far this question has traveled out of the seminar room and toward the laboratory bench. And it dovetails with something the cosmologist Max Tegmark has been arguing for years. I'm building computers that can play chess, that can process natural language, that can answer quiz show questions, that can drive cars, and so on. If I'm driving a car, I'm having a subjective experience of colors, of sounds, emotions, thoughts. But why does a self-driving car have any subjective experience? His mathematical universe hypothesis says reality is not merely described by mathematics and not merely modeled by it, but actually made of it. Pure mathematical structure all the way down to the bottom. And if that is true, then the question who built the universe quietly stops sounding like theology and starts sounding like a question for a software engineer. Who writes the code? Who builds error correction into the foundation? Who tunes the constants so finely that existence itself becomes possible? So we are left to holding 3 answers and a machine that just handed us a brand new way to ask the question. 3 answers. There are 3 serious ways to read everything Willow has shown us, and I am going to give you all 3 honestly, because the honesty is the entire point. The first stays closest to known physics. The universe is mathematical, and the structures we keep finding are simply features of that mathematics. Real but meaningless. No builder required. Mathematics needs no creator. It is eternal and self-consistent. And 2 plus 2 has equaled 4 in every possible world that ever could be. The elegance we keep tripping over is just the elegance of mathematics itself, nothing more. The second answer is bolder. The universe is a simulation, and those structures are the fingerprints of code. Reality runs like a quantum error correcting algorithm because it literally is one. The fine-tuning of the constants is simply a setting that somebody somewhere chose. And Willow, operating right down at the base layer of reality, is a probe dipped straight into the program itself. If that is right, then who built the universe has a literal answer. And it is not a god in any traditional sense, but something far closer to an engineer. The third answer is the one a growing number of physicists are finding hardest to wave away. We do not know. The patterns are real. The fine-tuning is real. The fact that a machine seems to compute as if reality were larger than a single world is real. But whether all of it points to mathematics, to code, or to something we do not yet have the words to describe lies just past the present edge of science. And sitting honestly inside that uncertainty instead of sprinting toward whichever answer feels most comfortable may be the single most valuable thing this entire moment has handed us. And notice something quiet about those 3 answers. 2 of them, the eternal mathematics and the simulation, sound like total opposites. A cold accident on one side and a deliberate creation on the other. But they agree on the one thing that matters most. Both say that underneath everything you can see and touch, reality is at bottom made of structure, of information, of math. They only disagree about whether anyone wrote it. And that is a far smaller gap than it first appears because it means the real argument is no longer about whether the universe has a deep hidden order. We can see the order now. The only fight left is about where it came from. Because remember what we have actually built here. Every single time human beings ground a new lens and aimed it at the unseen, the world turned out stranger than anyone had dared to guess. When Antony van Leeuwenhoek pointed the very first microscope at a drop of pond water and saw a tiny living thing swimming inside it, reality did not shrink. It exploded outward. Willow is that same kind of lens aimed not at the very small or the very large, but at the very deep, at the layer where physics dissolves into information and the universe becomes in some genuine sense a question asking itself. And it is only a prototype. Google's roadmap runs forward toward machines that would one day make Willow look like an abacus, and nobody alive knows what those will see. So here at last is the response that came back and why it was not what anyone expected. The universe did answer not in words, not in a sentence, not in anything our language was ever built to carry. It answered in patterns, in structures, in geometries that rose unbidden out of a machine probing the very edge of what reality allows. And every one of them looked less like an accident and more like something made. It looks like a masterpiece. The only question left is whether it had a master. So tell me before you go, of the three answers, eternal mathematics, a simulation, or honest uncertainty, which one do you actually believe and why? Put it in the comments because I read them and the best conversations on this channel start exactly there. If this story rearranged something in your head, subscribe and stay close because the next machine is already being built and the next question is even bigger than this one.